Modeling, it's not just for Calvin Klein. That's the title of our lecture number 2 in Sustainability Modeling for spring of 2013. Well, I thought I'd start the class with a little cartoon expressing the notion that models may have some answers, they don't have all the answers, and sometimes timing is of the essence. So models are there to help us tools in helping make better decisions, but they're not an end in itself. And I want to express that today, and we'll see the reasons for that in a second. Now, what exactly is it what we mean when we refer to models? I think it's important to better define this, at least in the context of this class. Most people have an intuitive idea of what models are, but in this lecture we're going to get into more specific details about this idea to formalize a definition about models. So a model is really a substitute for a real system. It's an abstraction that makes some assumptions and simplifications, and this is a really important point to make. Models are and should be used when it is easier to work with a substitute rather than with the actual system, and that's the whole point of having a model. Examples of this: an architect's blueprint, an engineer's wind tunnel, an economist's graphs. These are all models in the strictest sense. And models are useful when they help us learn something new about the system they represent. Now, the modeling process is can be rather involved, and it goes something like what is shown in this chart. You know, we have real events that stimulate our curiosity about a particular process or phenomenon. Okay, this curiosity can be translated into a questions or a set of questions about observed real events. These elements can be identified and form an abstract version about the real events. So there's an abstraction process that involves these assumptions and simplifications. And in many ways, these abstractions are hypotheses about how these real events are supposed to work in the inside. This abstraction leads to, when constructed, leads to the development of the model. Okay, and this model will yield some results that we can go back and check with the real events to see if the model makes any sense. And these conclusions and so-called predictions, and I'm going to put that in quotes, that we can extract from the model when compared with real events may lead to the rejection of the model, the acceptance of the model, or more likely some sort of revision. Okay. Now, this class focuses on a particular kind of models referred to as simulation models. Other ways you can hear them referred to are numerical models, computer simulation models. Now, if you look at this cycle that we just described, modeling is really a never-ending process. We build, we revise, we compare, and we change models. Because we're modeling systems that change over time, like the examples that we mentioned last time, the modeling process in itself cannot be considered a static process. It's a dynamic process in itself. It's always changing. Now, the case studies that look at this class provide some opportunities for building, testing, and using models. And each new case will allow us to learn about the system's behavior by using models to simulate it. I have a link here for Andy Ford's book on environmental modeling, which I partly used to prepare this lecture, and of which I'll talk a little bit in my commentary of this class later on. Now, the other thing is that we will be modeling systems. In a system, it's a set of interrelated components where any change in any component affects the set as a whole. Okay, so it's a connected set of components, and in order to study a system, we must know the components that make it up and how these components interact. What are the relationships that exist between them? The boundaries of a system, it's a key assumption made in defining the system. I mean, where does the system end? So putting some boundaries is going to be a key assumption, and we'll talk about that in the examples of this class. Now, can you think of any examples of systems as we go? Let me give you a few. You know what this is? An orchestra. A perfect example of a system. Each performer is a component, each instrument is a component, and the interactions produce this whole that is the system. A little bit more mundane examples. The car, okay, don't need to explain that. An ecosystem, again, each of these living organisms, each of the so-called biotic and abiotic components of the ecosystem conform the system of how it behaves. The human body, another example of a system. Many components interrelated so that they can function together. This is a little caricature of the global, sorry, the global economy. Okay, another interesting complex system. Now we're going to be using system dynamics to study systems, and system dynamics is a field of study, sorry, that was pioneered by Dr. J. Forrester in the 1960s, and he looked primarily at industrial systems, at companies and industries, identified their components, and formalized what's known today as system dynamics as a field of study. He later applied the same sort of set of principles to analyze the dynamics of city growth in the United States, and this led to another well-known book, Urban Dynamics, by the same author. That same group later applied these principles to develop the first world model, which was published in 1971, and that evolved towards the World 3 model that was published in 1972, and that we discussed during our brief introduction to the limits to growth work. But since then, system dynamics has emerged as a fairly interdisciplinary field. Now, this class is really about using system dynamics to understand, to study sustainability, because I think sustainability is an ideal field to apply system dynamics. I'm going to ask you to read this little wiki on system dynamics. There's a lot of history there, a lot of information that I think will be interesting for you. Now, how does this system dynamics approach work? So first of all, the word dynamics, it implies changes over time. So system dynamics is really a methodology for studying and even managing complex systems which change over time. So changing over time is a key element of the systems that we're going to be looking to. And sustainability, if you think about it, it's a concept that has time embedded with it. You know, when we think about sustainability, we immediately think, okay, sustainable over a period of time, and that's why these two concepts, system dynamics and sustainability, fit well with each other. We're going to be using computer modeling, and that will allow us to focus our attention on information, feedbacks, and loops that give rise to this dynamic behavior, to this change of the system over time. Computer simulation is particularly useful because it helps us understand the impacts of time delays, nonlinearities, and we're going to be defining all these terms. But these are all processes that lead to these behaviors that there are sometimes not intuitive or not obvious to understand. Now, I think I wanted to really point this out. We're going to be using system dynamics modeling for learning and understanding, not really for making predictions. And this is something that I want to make emphasis on, because sometimes people get caught on the trap of using models to make predictions, you know, quote unquote. And making predictions is using models. It's really a risky affair because, as we said before, models contain a lot of assumptions and simplifications that don't make them perfect. And trying to make a prediction based on these assumptions and simplifications is not really the purpose of modeling. The purpose of modeling is learning and understanding. And this distinction is going to become more apparent as we study these things, but I want to throw that out and get you thinking about this. Now let's formalize a little bit more this definition of a system by looking at the components. And systems really have four major types of components. We're going to call them stocks, fluxes, feedbacks, and lags. And I'll tell you a little bit more about this in detail right now. Let's talk about stocks. Stocks are also referred as the state variables, these represent the accumulation, that thereby the word stock, of materials or information. So a stock is something that changes over time, that accumulates, and when we say accumulate, it could mean positive accumulation, that means that it grows over time, or negative accumulation, that means that it decays over time. Okay? And so stocks are really conserved quantities, meaning that we can track their amount using a fundamental balance principle. Typical conserved state variables or stocks are population, water, land, energy, and other inventories that you can find. We will see this. These are not usual, but we will see stocks or state variables that are non-conserved. This means that these are really indicators of some aspect of the system's condition or behavior. And typically, a few examples are price and temperature. These are not things that are conserved that you can do a balance on them. But let me tell you a little bit more about this balance principle. And you have a system, okay, and this system has inputs, it has outputs, it has generation of stocks with them. So if you think about how do you keep track of the stocks within the system, you can invoke this general balance principle where if you take the inputs of the system and you subtract the outputs and you consider the generation of stock or state variable within the system, this balance will give you the accumulation of the stock. And we've talked a little bit about this already, and I think one of the examples we mentioned last time was your bank account, the human body weight, and others. Okay, so we're gonna be going fundamentally to this balance principle time and again in this class, because this is the underlying principle where the accumulation term on the right is the change in the system. Okay. The next component of systems are fluxes, and fluxes are referred to as controlled variables as well in system dynamics speak. And these are used to represent actions or changes in the state variable. Okay, now we'll go through some examples. Because a system dynamics model is dynamic, these control variables are used to update the state variables over time. So these are used to reflect how the system changes over time, how that stock is accumulated over time. Now the examples for these control variables are, in population, they're the number of births per period, which is a variable that changes the state variable population. Another example is the number of barrels of crude oil extracted, which would change the state variable oil reserves. Okay, we'll see some more examples of this. The next component of the system are feedbacks, and feedbacks are essentially interactions of system components. One component of a system will interact with another, and that generates a feedback. The changes in a system component initiate changes in the other components that in turn affect that component that originally stimulated the change. So that's how the feedback works. One component changes, it exerts this change or diffuses its change among the other components. These other components, while changing, affect the original changed component back. And that's how the feedback is generated. Now we can speak of positive feedbacks, and this is a change in the system component that leads to changes in the other components, which then reinforce the original change in the system. Okay, now let me give you an example. If you have a boiler that has a defective valve, that defective valve may not open properly when the pressure of the steam inside the boiler increases. And these boilers have these valves precisely to regulate this pressure. Okay, but if the valve's defective, it won't liberate the pressure. Okay, so when the pressure continues to increase, the valve continues to get stuck. It actually gets stuck more tightly because of the higher pressure, okay? And thereby restricts further the opening of the valve. So what happens is that you have a positive feedback in which one effect reinforces itself by affecting other components. The result of this is that the boiler ultimately explodes, okay, literally. And so positive feedback when uncontrolled results in what are referred to as explosive dynamics, okay? And this the boiler is an example, and so is the case of the population explosion, and we'll talk a little bit about that in the lecture about population. So that's an example, a couple of examples of positive feedbacks. Now we can also have negative feedbacks, and these exist if the change in the component leads to a response in the other components that counteract the original change. And the classical example is if you increase the density of a prey species in an ecosystem, you increase the prey species, this leads to an increase in predator density that in turn reduces the prey density. So what you have is essentially a self-controlling feedback, okay? The prey, you increase the prey, which leads to an increase in the predator, which then tends to decrease the prey. So you sort of keep things in check. So these negative feedbacks tend to counteract disturbances and lead systems towards what are called equilibrium or steady state. One possible steady state in the example that we were just referring to in the predator-prey population will be that the size of each of these populations sort of stabilizes in the long run, and then the system becomes sort of sustainable. Okay, and so we'll look at that example also in more detail later on. And these stabilizing dynamics are in contrast to the positive feedback, which tend to drive the system away from equilibrium by amplifying disturbance. Okay, let's see. Oops, sorry, I think I messed up there. But you see here on the left, the positive loops or positive feedbacks tend to amplify disturbances, so they're unsustainable or drive the system away from equilibrium. And the negative loops tend to stabilize over time. Okay. The next component is lags, and lags are used to in system dynamics to represent the fact that once a stimulus in a system occurs, the response to the system may not be instantaneous. So there could be a lapse in time, a delay between the stimulus and the response of the system. And in a real life example, and there was a power outage in the northeastern United States on November 9th of 1965. Okay, and this was followed by an increase in the number of births in that area 9 months later. This is true. This is based on data. You can look this up. Okay, so the 9 month is the lag between the stimulus, which was a power outage, and the response, which, well, I'll leave that to your imagination. You know what happened there. Now, how that power outage translated into higher demand for classrooms or school buildings 6 years later when the children were of school age is less obvious, and it's more complex because that depends on a larger number of factors, such as migration, behavior of families, the availability of teachers, the availability of public funds, among other factors. So these are a couple of examples of using lags to understand what could happen. And 9th month lag, in this case, worked pretty well. The 6-year lag, it's a little bit unclear. Now, I wanted to sort of talk about some basic principles of modeling, and this might sound a little bit, pompous, ostentatious, because it's really something that hasn't been formalized as principles. But I'll use the word principles more like strategies or guidance to modeling. Okay, so I've sort of outlined 10 steps for this modeling process, and we'll be coming back to this list as the class progresses, and to maybe challenge and refine some of these steps. I think the first thing to say is that system dynamics modeling is both science and art. It's not entirely formal. We're going to be doing a lot of things that are not necessarily mathematical, which tends to be confused with modeling at times. The philosophy, the approach that I've tried to make in this class is to make this modeling an open process and flexible so that anyone, literally anyone, can do it and understand it. Okay, and I think we'll get there. I'll reiterate, no model is perfect. It's not even close to perfect. But if we make clear our assumptions and our simplifications, then the differences in results or the errors that we make are easy to spot and to correct. Okay, so if we keep things clear, transparent, very open, very flexible, I think it's a lot easier to spot errors and mistakes and to really, be upfront with them. Okay. Now I want to follow these sort of 10 steps that I've outlined along with a specific example, just so the going through the steps is a little bit less dry. And the example that I chose for this was one of the examples that we discussed last class, which is the body weight. So let's look at our body weight, and this is a little bit of a slightly modified version of the body weight example we discussed last lecture. You have the system that consists of your body mass or the weight. You have inputs, food, liquid inputs. You have outputs, excretions, surgery, which I mentioned sort of half-jokingly last time, and we won't be considering that in this particular example this time around. And then you have possibilities within the system to affect the body weight, such as your metabolism, natural metabolism, and the exercise, which increases the metabolism rate. Okay. So let's go at step one. We have to define what you're after. Why are you doing this model? What is it that you want to understand about the system? What questions do you want to address? Okay, so you want to define your problem and the goals of the model. Okay, this defining what you're after, it's really important. And the sooner you do it, the better it is. And I see at times people just starting to go ahead and throw a model together without having a clear idea what they want to get to, and it's not necessarily that would lead to a wrong result or a wrong process, but it does waste time. Because you sort of start doing something without having a clear goal. So define your goals, define the problem, and frame the questions that you want to answer with the model. Okay. Sometimes the problem may be very large, or the system that you want to analyze too complex. So we want to maybe break it up into subsystems and try to set up individual goals or smaller goals, and go from the simple to the difficult, from the easy to the complex. And this is going to be a reiterative philosophy that I'll be coming back to in all the examples. So let's talk about defining the problem. And in this case, in our example, the problem, as I'll state, the problem is seeking a goal of developing a stable and healthy weight. Okay, so that might seem like a simple enough goal. Questions, what combination of diet and exercise will result in this stable and healthy weight? And by the way, what is this healthy weight that we're trying to reach? And these are all questions that can be answered by a model. Okay. The next step is to designate the state variables. Now, remember that by definition, these variables will indicate the status of the system. Okay. I will come back to this this principle time again. I like to call it the keep it simple, or what others call the KISS principle. Okay, and we're going to purposely avoid complexity in the beginning. The initial focus needs to be on understanding of the system. Another important note is to keep track of the units of these state variables. In units, when we do quantitative analysis, is extremely important, and sometimes actually you can spot mistakes just by looking at the units of the variables involved, and we'll look at this back in our example. In our case, in our example of the body weight, this state variable is the body weight itself. Okay, The units are kilograms or pounds. So that's essentially the definition of the state variables for this example. Our next step is to look at control variables, feedbacks, and lags. And these are the components that affect the stock. So these are the flows or controls into and out of the state variables. These are the inputs and the outputs. In many cases, in most cases in system dynamics models, these control variables are calculated from the state variables in order to up them at the end of what we call a time step. And I'll come back to this concept of time step in a second, but this is essentially periods of time or intervals of time during which we update the state variables, because these state variables are changing over time. At this point, it's useful to note which state variables are donors and which are recipients with respect to the control variables. Essentially, the direction of how these arrows point, which are inputs, which are outputs, where are these inputs and outputs coming in or out of, okay? We should introduce any lags in the system based on data, based on assumptions, based on knowledge about how the system operates. And again, we'll go back to noting the units of these control variables just to make sure that we're mixing or adding apples with apples. And we need to keep this simple at the beginning, especially trying to capture the essential features. And I think one comment that I'll make here is that with modeling, we need to be unafraid of making mistakes, because actually from making mistakes you learn a lot about the system and a lot about the modeling process. So in this class and in the examples that we'll say, you know, we're going to be making a lot of mistakes. Some will be intentionally, some not, but I'll guarantee you that in each and every case we'll learn a lot about the system. Now, in this case of our example, the food intake, and that could have units of kilograms or pounds, could be a control variable. Although more commonly calories, in the case of body weight, are the more usual control variable. Excretions have units of pretty much volumetric units, so milliliters, ounces, or liters. Metabolism has units of energy, essentially calories, you know, either intake calories or burned calories. Same with exercise. So metabolism and exercise are sort of in the same realm. They don't have the exact same dynamics, but they have the same units. Sometimes comparing units allows you to draw these analogies. So for example, metabolism and exercise, they both, for the human body, they both burn calories. They both reduce body weight, or tend to reduce body weight. Now, because this example is very simple, it's a single component system which has got one state variable, which is body weight. We'll assume that there's really no feedbacks, and because there's really no interactions between components, and we can come back to this assumption later. And another simplification is because it's a single system. There's really we won't consider lags for the time being. In practice, this means that the food and exercise are assimilated into body weight immediately. So, and I'm sure physiologically that's not true, but it allows us to set up a simple model and see what's going on. So I'm sorry, I think I toggled back. What do they depend on? Okay, so let's take a look at, in this example, at the parameters. And let's assume, for the sake of an initial model, the food intake of your body weight is 2,000 calories per day. Liquid and excretions, the net, so the net liquid that you ingest minus the excretions is roughly 0.2 liters or 200 milliliters per day. That the metabolism burns 1,800 calories per day, and that your exercise is roughly 400 calories per day. Okay, and here are some notes to explain these a little bit. First notice that in addition to these parameters, you'll need an initial condition for the state variable. So you need to know where you're starting your stock. In this case, the body weight. Also, because you're dealing with different units, you will need to convert, calories and liters to kilograms, which is kilograms are the units of your state variable, of your stock. So you're going to need conversion factors or converters, and this converters is common language for SD modeling. And some of this data I pulled out of a couple of references that you can look up online, from WebMD and from NutriStrategy. So this, so far we have, the model. We've defined the stocks, the control variables, and we've defined some parameters. So the next step is what's referred to, or I refer to as the foolproof check. So the idea here is to check the resulting model for any possible violations of physical, economics, laws, and principles. Gravity, conservation of mass, energy. Things that are obvious that shouldn't be violated, just as a foolproof check. This one is big, and I emphasize this. This is the point at which you make sure that you're mixing apples with apples. That means that you have consistency in your units, and this is extremely important. This is the perfect spot in the model for checking this and making any corrections. There are some nuances, and when you do some math, you want to check for possibilities of dividing by zero, which won't be allowed. Variables that turn negative, that shouldn't turn negative, like volumes, prices. If this is the case, you may want to introduce some conditional statements to avoid these violations. So there are ways to avoid these violations that you can hardwire into the model, and we'll be doing that in system dynamics. So in our model for your body weight, you have the stock, which is the body mass. You have inputs, food and liquid. You got outputs, excretions, surgery. We're not going to be looking at surgery in this example. You have sort of feedbacks or other control variables like metabolism and exercise. And there will be other information that's needed. And in this case, the initial weight, let's start with 80 kilograms for a person. Converters. This is the first converter between kilograms and calories, and this is roughly for food intake and exercises. A kilogram is roughly equivalent to 7,700 calories, sort of the mass energy conversion. Another converter is based on the density of the liquids, and let's assume that density is 1, meaning that kilograms is about a liter. For all liquid intakes and excretions is very simplified. Then the next step, once you have the model, you've parameterized it, you sort of foolproofed it, or at least there's nothing obvious there that shouldn't be, then you make what's called a dry run. Okay, you choose some time horizon over which you intend to quickly test the dynamic behavior of the model, and you choose a length of time interval. This is what we refer to as the time step, for which these state variables are being updated. And then you check the computation over a few of these time steps and look at the variation of the state variable before running the model, okay, before actually running the full thing. Okay. So in this case, let's say that the time horizon is a year, okay, so you want to look at the body weight for over a year period, and you're going to be updating your model results daily. This could be monthly, but for sakes, because a lot of the food intake data and a lot of the exercise data is given in daily values, it's just as easy to update the model daily. So one day or daily is going to be our time step. So if you think about the accumulation principle or the balance principle, it's very simple to understand that the body weight after a period of time equals to the initial or the before body weight plus the food intake plus the liquid intake minus the excretions minus the metabolism minus the exercise. So if you add all the ins and outs, you get the accumulation. And you can do an example calculation. So the body weight after 1 day, um, it's the initial body weight, which was 80 kilograms. Then you have the food intake, which was 2,000 calories, and you convert that to kilograms using the conversion factor of 7,700 calories per kilogram. Then you have the sort of the net liquid intake, which is essentially the net between the liquid intake itself, water, juice, whatever it is you drink, minus the excretions. Okay, and you convert those liters to kilograms using the conversion factor. Then you have the metabolism, the 1,800 calories, okay, converted to kilograms, and then the exercise, which is the 400 calories converted to kilograms. So if you do that and you run a simple calculation, so I encourage you at this point to get your calculator, crunch these numbers, and you get the body weight after 1 day. You started with 80 kilograms. After 1 day, you're 80.17 kilograms. Okay. And you say, well, does this make sense? Well, it's it went up. It went up by a little bit, probably realistically, and this matches weight gains over a day very well. So there's a sort of a sanity check here, and you say, well, this makes sense. If I had received the final result of 90 or 65 kilograms, I'd say there's no way this can happen over a day. And there's something wrong, and then you go back and look at your parameters or you look at your model and see what's on. But so far, this looks reasonable. So then we go ahead and run the model, okay? And then and you see, you graph the results and you see if these results make sense. You can start then playing around a little bit with the model, trying to change things to see if the model is robust. You can choose, for example, different time steps. So let's say you want to do not daily, but weekly, or maybe sub-daily, time steps, and you can think about possibilities there. You can choose you can choose alternative numerical solution techniques, and I'll explain these later. But these are essentially the way you make the calculation, how you add up things, and there are different ways of doing this, as we will see. Now, for example, you can half the time interval, or you can double it and see if the results are the same. Okay, and that's a good way to check whether the model is running properly. So in our case, I basically ran the model a little bit, and I ran this with no software, and I just developed a little spreadsheet, which is in the Dropbox folder in this class, and you can use it and play around with it a little bit more. So you see here, this is the monitoring the results over 10 days, and this is really in terms of stabilizing the weight, this is really going very well. You can see that the weight is increasing steadily. So this regime appears to lead to body weight dynamics that are not sustainable. Okay, so you're gaining weight, or this body is gaining weight really quickly. So that might mean if the calculations are correct, okay, which is in this case they are, then this behavior of the model may indicate that there's something about the assumptions, there's something about the simplifications that we've made that's not really there. Okay, and we're going to go back to this example and see how we can fix it. But I want to get you to think about it some more. The next step would be to push the model to what I like to call extreme. So try to vary the parameters to the reasonable extreme. So push them up, push them down to see if the results in the model still make sense. And if not, you can go back and revise the model to repair these errors. And you will see that these errors are fairly easy to spot once you gain some practice. And The next step then it's to compare, if there's any data out there, benchmark the model, and the idea is to compare the results with any sort of experimental data or any empirical information. In the case of body weight, for example, you can go and check against if you monitor data on the body weight over time, if you have data on the daily body weight of an individual, then you can go back and say, well, the model compares favorably with the measured data. So that's again, it's a sanity check. It's not a foolproof check, but it's a sanity check. Um, and sometimes this means simplifying the model further. Maybe have some lab experiment for which you have data. You have some limited piece of information, and one of the most useful utilization of models is to fill in gaps when you don't have data. And so sometimes you use models when you don't have enough data, or when your data that you have it's got errors, or it's got holes in it, and it's a complement. So I don't think it is ever a substitute for real data, but it's something that actually can be used with data to enhance your understanding and your knowledge about the system. Okay, so that's another lesson that I'll throw out there, and that will come back time and again when we look at the different systems. And the last step is you revise and you iterate, and modeling, it's in essence a revision and iterative process. You can go back, revise the parameters, maybe even revise the model, change some feedbacks, change some relationships, change some assumptions, and basically done to reflect greater complexity, and to maybe try to meet exceptions to the results that you're trying to simulate. It may allow you to frame a new set of interesting questions. Once you have a working model, the nice thing, if you have a model that you're fairly confident that it's working, is that you can start asking, okay, so what if I start sort of the what if questions? What if I start, dieting more, exercising more, or changing my exercise routine, etc., etc., etc. And as the system gets more complex, the questions also get more interesting. And in step 10, really, it's about going back to step 1 and revising everything until you get something that you're comfortable. At this point, I'll ask you to think about what will you change in the example of the body weight, and make any guesses, or even better, if you can calculate the results. And if you have any insights or understanding, I want you to post them on our Facebook page, so that we can share our understanding and our knowledge, or any insights that we might have. Now, there are other things to keep in mind, besides this 10-step process. First of all, don't worry about applying all these steps all the time. I mean, these steps are essentially guidance steps. It's more about getting you to follow a path, and you'll start making your own tricks, and you're developing your own skills. However, I find it useful, and I do this myself. Every now and then I go back to this list and see, and I've revised this list. This list used to have like 7 steps before. Now it has 10, and it might be condensed to 9 or to 8, and some of the contents of the steps may change. But you need to develop your own strategy. Modeling is also a little of a personal exercise. Now, in this class, we're going to be using the system dynamics, the models and approach to experiment and to forecast outcomes. I'll go back to the issue of not making predictions. So this is really not about predicting anything into the future. It's more about asking further questions, try to pose scenarios, and see where the outcome would lead if that were the scenario. Okay, this overall allows you to learn more about the system. So we'll talk about next week. Next week we're going to be using a tool called Vensim, the software, which you should have downloaded. And it's essentially a graphical programming software that allows you to uh, do all this graphical interface, all these boxes with the arrows and the feedbacks in a very intuitive fashion. And doing this will allow us to build a system dynamics model of increasing complexity. Now, as we develop these models, we'll be introducing um, in more detail these general principles that underlie the respective disciplines. So when we look at population, we're going to be looking at more about demographic principles and how these principles can be translated into the system dynamics framework. And this will enable us to pursue better investigation of these systems and to ask and answer questions of about about the dynamics of these increasingly complex real-world phenomena. And I'll encourage you just to get a better understanding of system dynamics to look at this website of systemdynamics.org. I think there's a lot of good material there, not only about about the field, but also about the fundamental concepts that I think you'll be able to assimilate. So with that said, I'll leave the lecture there. Please watch later the commentary that I make, which I think complements well this lecture. So long, and I'll see you next time.